Good day from Chem Help ASAP. In this video, we'll perform an oxidation of an alcohol, the OH group in benzoin, to form a diketone, benzil. We will discuss different alcohol oxidation reagents, talk about the reaction, perform the experiment, isolate the crude product, and characterize the final material. Let's briefly discuss alcohol oxidations. What happens in an alcohol oxidation? We are going from a carbon-oxygen single bond to a carbon-oxygen double bond. We have formed a new pi bond. Reactions that form new pi bonds are often elimination reactions, and indeed many alcohol oxidations are actually elimination reactions. Specifically, they are very similar to E2 reactions. What are the reagents for these oxidations? You can use PCC, pyridinium chlorochromate, Swern, oxidation conditions, which is a cocktail of several reagents, as well as other possible oxidation reagents. Without going into the mechanism, both the PCC and the Swern oxidation react with the alcohol, place a leaving group on the oxygen, and provide a base that breaks the CH bond, forms the CO pi bond, and kicks out the leaving group, just like an E2 reaction. This is the reaction being demonstrated in this video, the oxidation of benzoin to benzil. The oxidant for this reaction is nitric acid. Why not use PCC? PCC generates a lot of waste that can be a hassle to remove. Why not do a Swern? The Swern requires multiple reagents, which often need to be purified for the reaction. So instead, we are using nitric acid. Nitric acid is particularly convenient because A, most labs have a bottle of concentrated nitric acid somewhere in an acid cabinet, and B, excess acid is often easy to remove at the end of the reaction. Nitric acid is an interesting acid. Nitric acid is often not used in organic reactions. HCl and sulfuric acid are common, but nitric acid is not. A reason for nitric acid being less often seen is that nitric acid is not just an acid, but also an oxidant. When heated, nitric acid can form nitronium ion. Nitronium reacts with the alcohol to make a nitrate ester. I'm not 100% sure of the mechanism of this last step, but I suspect this could be an intramolecular elimination to form nitrous acid, HNO2, and the desired ketone. The oxidation of benzoin with nitric acid is a commonly cited reaction. I'm following a procedure from Louisiana Tech University, go Bulldogs, from the link at the bottom of the screen. I have modified the procedure a bit, but it is essentially the same as contained in the link below. Combine nitric acid and benzoin, heat the reaction for a bit, add water to isolate the crude product, and recrystallize to get clean material. Okay, let's get started with this reaction. The first thing we're going to do is weigh our benzoin. And here is a weighing paper. I'm just going to fold over some corners to give this paper a little rigidity. Okay, great. And we want 4 grams. 4 grams of benzoin. Benzoin, look at this bottle. This bottle's ancient. Like all good old bottles, it has bits of parafilm all over it. But this is almost a historical artifact. So we need 4 grams of this. I'm going to tare the balance. And I'm going to use my favorite method, just tap, and we're going to get about 4 grams. You know, if I'm 4.1 or 3.9, that's fine. This doesn't need to be exact. We just want to make sure we record exactly what we use. I don't know why I'm going, oh, there's a big chunk. Okay, I'm going pretty slowly. That's only a little over 1 gram. That's a lot. Okay, we are at 3.6. Slow it down. That's a big chunk. Okay, that's going to do it. That is 4.070 grams. And that will work. And we will take this to the hood, mix it with our nitric acid, and begin this reaction. Okay, we are now in the hood. And this is going to be our reaction flask. It is a 50 milliliter Erlenmeyer flask. There's a little bit of a chip there, but that'll be okay. So I'm going to put this on our hot plate. So our hot plate is set to 125 degrees. We want this close to boiling at about 100. So I'm going to set it a little higher because sometimes you don't get good heat transfer through that glass. So I have a little bit higher than what I really want the reaction temperature to be. And into this 50 milliliter Erlenmeyer flask, we are going to add our freshly weighed out benzoin. And I'm going to use a powder funnel because that's a lot of stuff to fit into that little opening. I think that's pretty good. And I don't know why I put that down because I'm going to move it again very quickly. So what else we're going to mix in is 15 milliliters of concentrated nitric acid. So concentrated nitric acid is 70% nitric acid. It's really quite potent stuff. So if you get this on your hands, of course you want to get it off your hands quickly. Many people would say you absolutely must wear gloves. I don't wear gloves as much in lab as I should, but I tell you what, one thing I am wearing right now are my safety glasses, because nitric acid, you don't want to mess around with your eyes with any strong acids or bases. So you have to wear good eye protection always in lab. Okay, so I'm just pouring that in. That's 15 milliliters. That is concentrated nitric acid. Let's go on to the hot plate. Let's stir that a little bit. And goodness, that's it. So I have a little bit of agitation going in there, which will be fine. I am going to, since I'm heating it, I'm going to put a little watch glass on top. And we're just going to let this heat and stir. Now, the procedure says 10 minutes. In my experience, we might need longer than that, but we will come back in 10 minutes and see how it looks. But right now, on the first edition of nitric acid, there's really no change. It just looks like a white solid in a clear, colorless liquid. We'll see what happens within 10 minutes. Well, what a difference just a few minutes makes. It's about 10 minutes later, and as you can see, this whole thing is extremely dark with this brown vapor. And after probably 2 minutes, it was very almost a yellow color in here and still looked white at the bottom. But now we've generated a lot of this vapor, and it's gotten super dark. And you see, I'm capping it. We can let that open up. And these are nitrogen oxides that get formed from the reactions that involve nitric acid. So what's happening here, and I can't totally show it, but everything is melted. The solid is completely gone. And this looks cloudy at the bottom. Let's come in a little closer if we can. It doesn't help too much. But this is a biphasic mixture. There's the aqueous acid layer, and then there's the melted, probably mixture of product and starting material layer. And so what I'm going to do is I'm going to sample this reaction. I'm going to let this take it off the hot plate. I'm going to let it settle so that the oily layer comes to the top. And I'm going to sample that oily layer, and I'm going to look at that by TLC, and we'll be able to monitor and see if we still have starter material or not in this reaction using a 3-lane TLC plate. So that is the plan. Okay, I want to say one more thing about this 3-lane TLC plate. So we're going to sample the material out of here, and this uses a technique I call it a mini workup. I don't know what other people call it, but I have a little test tube here. And this test tube, I'm not sure if you can see, but there's a lower layer that's just water, and the top layer is ethyl acetate. Now when I TLC this mixture, I don't want to put all that acid on my TLC plate. So I'll just get a small drop out of this reaction mixture, and I'll put it in this mixture of ethyl acetate and water, and I'll let that mix around. all the acid will go down into the aqueous layer, and that'll leave on the top layer just the organic compounds like unreacted starting material, hopefully the product, and maybe some impurities. So this doing a little mini liquid extraction, which I'm calling a mini workup, is how you can separate some of the aqueous materials from the more organic materials. So I'm just going to touch this to the surface. You can see there's definitely some junk in there. Let's tap that in. Let the ethyl acetate mix around. And now I'm going to swirl this around a little bit, give a chance for the acid to go in the aqueous layer, and let the organics stay up top. So as you can see, there's some yellow color, so it looks like we have some organics in the ethyl acetate layer. That's what we're going to spot on the TLC plate, and hopefully most of our acid has gone to the bottom so it doesn't affect the performance of the TLC plate. So let's go run this TLC. I'm going to run this in 20% ethyl acetate, 80% hexane, and we'll see what kind of spots we get. Okay, I hope this comes out okay on the camera, but here's the TLC at 10 minutes. Here's our starting material, and you can see across from the starting material, we still have starting material in the reaction, but we have a nice big spot. That's likely our product. Less polar, so it rises more on the plate. But we do see a couple impurities, and we'll just have to monitor those. But at 10 minutes, this isn't done. So it's taken me about 10 minutes to run this TLC plate. So let's go ahead and run another TLC and see if the reaction has made any changes. And we are back in the hood. This is about 20 to 25 minutes into the reaction. I am ready for the next TLC plate. I just wanted to show the reaction. Still looks brown, looks about like what it did at 10 minutes. Maybe the brown's a little lighter, maybe not, but it's, you know, it's still doing something, and we're still generating this brown gas. Okay, again, I hope this comes out on the camera. So at the bottom, this is the previous TLC plate. Here's the next TLC plate. Honestly, it doesn't look ridiculously different. So there's our product forming. There's our starting material. Maybe in terms of relative intensity, we've got a little bit more starting material in at the 10-minute plate rather than the 25-minute plate. But this is still going. And honestly, the reaction looks kind of the same at the moment. And right now we're probably about 35 minutes in. So I'm going to go ahead and run another TLC plate, and we'll see what happens. Okay, we're about 30 to 35 minutes in, and I think this does look a little fainter in the coloration. So maybe that's a sign that we're getting some progress, but based on the TLC, it's still going. So let's go ahead and take another TLC, get that third TLC plate, and just see where the reaction's at. Okay, third TLC. Okay, so here, this is at 40 minutes. Here's our product. Here's our starting material. It is starting to get really faint in here. Now, let's turn this off and take a walk over to the hood and see what we have here. You notice this is quite a bit lighter now. The brown color has tapered off quite a bit. So I think this is really essentially complete. Just to be sure, I am going to take one more TLC plate, but unless it shows you surprises, I won't show that on camera. We'll show it later when we talk about the final TLC, and we'll go ahead and move forward with this reaction. Alright, so this last TLC actually looked pretty good. We'll discuss it a little bit later. This is now off the heat. It's still smoking a little bit, but again, I'm not sure how well it shows up, but there is kind of this biphasic layer. There's an aqueous layer on the bottom, and then a layer of our product on the top. It's still melted. So what we're going to do is we're going to take this and we're going to pour this into 75 milliliters of water in a 150 milliliter beaker, and we're just going to dump it in straight away. And you can see the cloudiness, so no surprise, our product is not very soluble in this aqueous mixture, so we get very cloudy. It's to be expected. I'm going to use just a little water in here to rinse this out. And now we'll let this stir. Toward the bottom, you can see that there are some clumps forming. So this is our product, probably formed in oil dispersion as we mixed it in. And now those oil droplets are coalescing, it's cooling off, and we're getting solid formation. And of course, that this is a crude solid, all the impurities are trapped in there as well. but at least we're isolating our crude material. Once this is done stirring, we'll filter this, and then we'll work towards a purification of this crude material. This has been stirring for some time now, but probably close to an hour. Let's turn off the stir. It still looks a little bit cloudy, but if you stop the stir and you see it settle out, you can see that's actually fairly clear. So any oil that has not been soluble has coalesced and it's become a solid, and it looks really good. So what I'm going to do is I'm going to use this Buchner funnel, and we are going to filter this as our crude product. And this is essentially a water solution that we're filtering. So I'm going to seat the filter paper with water. Great. And that's drawing through. And now let's let that stir bar get everything nice and suspended. And then let's just filter away. And I think you can see this is going to be, looks like a yellow solid. Let's see, impure crude material is yellow. Okay, not perfect, but I think good enough. That's a pretty good transfer. So this is now our filtered product. I'm going to let this dry a little bit, but based on the TLC, we kind of expect to see some impurities in here. There are at least 2 impurity spots. There might be a speck of starting material left over. So we will need to recrystallize this, and the procedures that people follow for this reaction do indeed involve a recrystallization. So that is the next step. Alright, you can see I've taken our filtered solid and put it on a weighing paper. I don't have a mass on that, but it's a pretty good amount of material. Remember, we started with 4 grams of benzoin, and we ought to get roughly 4 grams of benzil, a little bit less. So that's a lot of material. Now what I have on the stir plate is 10 milliliters of ethanol. So I'm following a procedure that calls to dissolve this into 10 milliliters of hot ethanol. I have the hot plate at about 110, and I don't think the ethanol is fully up to temperature, but I'm going to add this material into our ethanol and just let that stir and heat, and we're just gonna let that dissolve as that gets hot. So this will probably take a little bit of time to heat up, but it's my impression that this should dissolve in ethanol, and what we're going to do afterwards is we will add water and get this to begin its oiling out. But we have to let this heat up, dissolve first. Okay, this looks really nice. This is all dissolved. This is the product dissolved in 10 milliliters of hot ethanol. And now I'm going to take some of this water, and the procedure says to add water until you get to the cloud point. So this is stirring pretty vigorously. No, not really vigorously, but vigorously enough. I'm just going to add in water. And I'm not sure how well that shows up on camera, but when you add water, it kind of clouds up, and then as the water mixes in, everything goes clear again. Okay. I'm trying to add slowly because I want to add slowly, but if this is going to take a lot, I don't want to go too slowly. Okay, that's about 2 milliliters of water. Keep adding until it gets cloudy. That cloudiness is more and more persistent. It's almost a titration. We're kind of titrating the solubility. Boom. Oh, okay. Well, that's cloud point, and that's solid. Okay, bam. So that's far enough. So now, once we hit the cloud point, we just let this cool. And as you can see, we're solid. So let's turn this off. Let this cool. I would guess that stir bar is no longer doing anything. Let's now let this cool, and once it cools close to room temperature, I'll go ahead and put it on ice. We will get some absolute ethanol also cooling, and then we'll be ready to do a filtration of this product, and hopefully it'll be pretty clean. Well, everything has cooled down, so I have on ice our solidified product. That's not all solid. Remember, there's ethanol in there. There's some water in there, and we have some cold ethanol water. This is about a 30% water, 70% ethanol. I tried to dilute the ethanol with some water in a similar proportion to what we used in with our crude product for our recrystallization. And then of course we have a Buchner funnel, and we're going to filter this solid. So let's go ahead and make sure everything's set up with our vacuum and our trap. And let's use some of this solution to seat our filter paper. There's a little filter paper in there. So that's wet and seated. And now we need to filter this. And this is a little adventure because we're going to have to break this up. This happens sometimes in precipitations. I want to work with this quickly because I've got a hunch that this has pretty decent solubility as it warms up. So let's try to get this broken up quickly. That's a lot more loose now. Now there is a stir bar in there. I'm not going to pretend that I'm going to get that out of here right now. We'll get that out at the end after we're done with the filtration. And let's do our best to scoop this right out. Come on. Sometimes they come easy, sometimes they come hard. You just got to keep working at it. And as you can see, I'm spreading this around pretty good. I don't want to do that, but it's just what you have to do. So we're mostly transferring this all in the funnel. That's good. It's nice white material. I'm trying to smush it around down in the funnel to make sure all the liquid gets drawn out. Now we have our cold solvent. Let's use this as best we can. So that's already looking much better. Let's try one more of those. Sometimes these are terribly difficult, and sometimes they're really not that bad. I'll be honest, that wasn't as terrible as I feared. So that's good. Let's go a little more. And we'll just put a little more in here just to try to rinse out this filter cake that we have. And I'm pressing down. Now, as you can see, there is some yellow color down here. And that yellow color, it could be that our product is yellow and we've lost a little bit. You always lose a little bit of product in recrystallization. We can't avoid that. But let's go ahead, take a peek down here. So that's a pretty nice looking I could have smushed it against the edges a little bit better, but that's not terrible. So now I'm going to leave this on the funnel. I'm going to let that dry, and once it's dried, we'll put it on a piece of weighing paper, and we'll find out what the what our recovery is for this recrystallization. It is now a day later, and here is our dry material. This is 3.377 grams of recrystallized product, that is benzil, formed by the oxidation of benzoin. And that's going to be a pretty good yield. Of course, anytime you want to talk about the yield, you have to talk about purity, and the characterization data will either back up my claims that this is clean, or it'll undermine my claim. So we'll just have to see what the characterization data say. Before we wrap up, I want to point out one other thing. So here is my finger, and I don't know if you can see what my finger looks like, my thumb a little bit too. There's a little bit of yellow on there. Like my other finger doesn't look like that. So this finger's a little yellow. So what happened there? Well, what happened is I worked with nitric acid without wearing gloves. And nitric acid, when it gets on your skin, it'll turn it a little bit yellow. So here I'm right-handed, I'm using my index finger and thumb to grab things, and something had a little bit of nitric acid on it, and that discolored my hand. Now, this didn't hurt, it didn't burn, it didn't irritate me, but this is definitely a chemical exposure effect. So just beware. Sometimes you feel like you're not getting stuff on your skin, and it doesn't matter. And sometimes the chemicals will tell you otherwise. So that's and that happens sometimes when you work with nitric acid. It will yellow your skin. Okay, so let's take the next step and let's look at the characterization data. Let's start our review of characterization data with the TLC. On the left is the TLC of the recrystallized material. It looks like one spot, but there are two very faint spots in here. So the mobile phase is 20% ethyl acetate, 80% hexane. The product has an RF of 0.38. The two impurities are 0.29 and 0.21. On the right side is the recrystallized material next to the last TLC of the reaction at 50 minutes. You can see the product and 3 other spots in the reaction. The spot at 0.21 is the starting material. So there is some starting material in the purified product. That's fine. The product is not 100% pure, but the TLC is pretty nice. How about the melting range? The literature melting range is 94 to 95 degrees Celsius based on sigma Aldrich. The experimental melting range is 92.5 to 94.2 degrees Celsius. That's fine. So far, both the TLC and melting point look pretty good. Let's see what the NMR says. Here is the full NMR spectrum. The spectrum was run in DMSO, so we see DMSO at around 2.5 ppm and a bit of water at 3.5 ppm. The field strength is 400 megahertz. Benzil is a boring structure with just 2 aromatic rings, 10 CHs. That's all we see peaks in the aromatic region. Let's zoom in closer. Here is just the aromatic region. The ratio of these peaks is 1 to 2 to 2. The 1 is the parahydrogen. The doublet 2 is for ortho. The triplet 2 is for meta. The ratio is 1 to 2 to 2, but the actual number of hydrogens is 10. So these integrations are actually double. 2 to 4 to 4. If we widen the view and continue to zoom in on the vertical scale, we can see the impurity peaks more clearly. These little aromatic impurities are almost certainly the extra spots we're seeing in the TLC. Since we heated this reaction for a long time, nearly an hour, in nitric acid, I wouldn't be surprised if the main impurity weren't nitration of the product. Regardless, the NMR spectrum is fairly nice. The NMR, TLC, and melting point all indicate clean product. Let's calculate the reaction yield. Here is our reaction again. So we used 4.070 grams of the starting material. The molecular weight is 212.25 grams per mole, so we used 19.2 millimoles of benzoin. I haven't performed the calculation for nitric acid, but we have a large excess of nitric acid. So benzoin is our limiting reagent, and 19.2 millimoles is our theoretical yield. For the product, benzil, we obtained 3.38 grams of product with a molecular weight of 210.09 grams per mole. That would be 16.1 millimoles. That is our actual yield. Actual over theoretical times 100 gives us the percent yield, 84%. That's a great yield. I have performed this reaction twice. The first time I got a 55% yield. I was not as careful with keeping the solvents cold during the filtration after the recrystallization, and I suspect I redissolved some of the material. With the second attempt, which is shown in this video, I was more careful and got a better yield. So this is a nice demonstration of an alcohol oxidation. Nitric acid is not the most common alcohol oxidant, but it works well with benzoin to give a high yield of clean product. I hope you enjoyed seeing this oxidation of the alcohol in benzoin to form benzil. Please subscribe, like, or leave a comment. Take care.